We will find keywords in our question statement, and we're going to use those keywords to answer all our questions. So in the diagram, ABC is a tangent. So tangent is a keyword. We know that we have the tan chord theorem. So tangent is a word we are interested in. So I have tangent. And then it goes on to say that F, E, and D are points on the circle. EF is equals to BF. Let's write that down. EF is equals to BF. I think that's all. Let's see if we can use these keywords to answer our questions. 8.1. Determine with reasons the size of the following angles. We have angle E1. Angle E1 is right here. Let's see if we can use the first keyword to determine the size of angle E1. The first keyword is tangent. So I'm thinking tan chord theorem. Well, my tangent is ABC. And between ABC and line FB, that chord, there's an angle of 32 degrees. That angle should be equal to the angle subtended by that chord at the circumference of the circle. So now we can say that E1 is equal to angle ABF. Why are we saying that? This is the tan chord theorem. Angle F given reasons. So let's go ahead and highlight angle F. We have said that angle E1 is equal to 32 degrees. But I want you to realize something. Our second keyword, EF is equal to BF. Angles opposite equal sides. So E1 is equal to B1 because those two angles are opposite equal sides. So they should be equals to each other. So if E1 is 32 and B1 is 32, it will be easy to find the size of angle F using the sum of angles on a triangle. So we're going to have 2E1 plus angle F being equals to 180 degrees. This is the sum of angles on a triangle. So angle F is equals to 180 minus 2 multiplied by 32. 2 multiplied by 32, that is 64. So we have 180 minus 64, which is 116 degrees. So that is the size of angle F. And then after angle F, we are now looking for angle D. Angle D is right here, far away from all the other angles. Looking at E, F, B, D, that is a cyclic quadrilateral. F plus D, angle F plus angle D should be equals to 180 degrees. This is because the opposite angles of a cyclic quad are supplementary. So D is 180 minus 116. We know that this is equals to 64 degrees. So we have the size of angle D. Let's see what else we need to find. We need to find the size of angle O1. So O1, it is at the center of the circle. Well, without thinking too much, the angle at the center of the circle is twice the angle on the same arc that is on the circumference of the circle. So that is our angle D. So what are we saying? We're saying that O1 is equals to 2 times angle D. Angle at center is 2 times the angle at the circumference. They have to be in the same arc or subtended by the same chord. So O1 is 2 multiplied by 64, 120, and 128. So O1 is 128 degrees. The last question, we are looking for E2. So right, let's go ahead and see what we have for E2. Well, at this point, we know fully well that O1 is equals to 128, but OB is a radius and OB QE is also a radius. So E2 is equals to B2 because angles opposite equal size. 2E2 plus O1 is equals to 180 degrees. So 2E2 will be equals to 180 minus 128. Everything we're dividing by 2 on both sides. So let's just go ahead and show that. If we do that, then E2 is equals to 26 degrees.
Look at how interesting 10.4 is, given that CF is equals to 6 units and AB is equals to 24 units. Let's calculate, given reasons, the length of AE, right? But then before we do that interesting one, let's just go through 10.1 first. So 10.1, right? So before I start answering these questions, I like going through the question statement so that I can jot down a few keywords, right? And then let me just do that before I answer 10.1. It says that in the diagram, BE and CD are diameters. So I have diameters. Why am I writing that down? Because I know that there's something special about a diameter, right? It subtends an angle of 90 degrees. And then of a circle having M as center, so I have center. Why am I interested in center? I know that the angle at the center is twice the angle at the circumference, right? And then chord AE, so I also have chord. And what else do I also have? I have two lines that are perpendicular to each other, right? 10.1, it says that let's give a reason why AF is equals to FE. So why AF, yes, AF here, it is equals to FE. They're equals to each other because the line from center is perpendicular to the chord. So 10.1, we're saying that the line from the center is perpendicular to the chord. If the line from the center is perpendicular to the chord, that line is going to bisect the chord, right? And that is why we say that AF is equals to FE, aka theorem number 1. And then 10.2, let's look at what 10.2 is saying. It's saying that let's determine, given reasons, the size of M1 in terms of X. So where is M1? M1 is right here, right? And then now let me go and look at my keywords and see if I can determine M1 using my keywords. It has nothing to do with the diameter, so I cannot use that, right? And then now let me go to center. Okay, it's easy to see that M1 is an angle at the center, and it should be equals to twice the angle at the circumference, right? Provided they are from the same arc. So M1 is being subtended by arc CE, so to say, and then that arc CE is also subtending angle A1, right? So we can go ahead and say that M1 is equals to 2 times A1, you know, angle at center is equals to 2 angle at circumference, right? That is 10.2. But we need M1 in terms of X, right? So if we find A1 in terms of X, then we have M1 in terms of X. So let me show you something. A1 is in triangle ACF, right? We have X here, as you can see, and here we have an angle of 90. So we can find the size of A1, right? A1 plus C plus F. This is in triangle ACF. This is equals to 180, right? Sum of angles in a triangle. So A1 will be equals to 180 minus F is 90, right? So minus 90, and then C1 is X. So A1 is equals to 90 minus X. So M1 is equals to 2 multiplied by 90 minus X, you know, and that should be equals to 180 minus 2X. So there we are. We have the size of M1 in terms of X. And now moving to 10.3, we're almost at 10.4 now, the interesting question. So 10.3 is saying that let's provide given reasons that AD is a tangent to the circle passing through A, C, and F. These questions can be a bit challenging, right? But then the best way of doing them is drawing the circle through ACF so that you can have a bit of clarity, right? So let me just go ahead and try do that and see what happens. So we need a circle that is going to pass through A, and then it is passing through C, it is passing through F, right? So something like that. My circle doesn't look too cute, but that is fine, right? It gets the job done. So we need to prove that this line AD is a tangent, right? We need to prove that AD is a tangent, right? We know fully well that if AD is a tangent, then this angle here, we have A2 here, let's not forget. This angle here, A2, should be equals to this angle X, right? Why should that be true? That should be true because of the tan chord theorem. So if we prove that A2 is equals to X, then we have proved that AD will be a tangent to a circle that goes through ACF. Right, so what is the size of C? The size of C is equals to X. So now we just need to prove that A2 is also equals to X. Let's go back to our keywords. We have used center. Let's see if we can use the chord. I don't see an immediate way of which we can do that, right? But then I'm open for correction. But I can see a way where we can use the diameter. Let me show you how. We have the diameter CD, right? And then it is subtending this entire angle. Oh, my sketch is getting messy right now. So this angle here should be 90 degrees if it's been subtended by CD, by diameter CD, right? If that angle there is 90 degrees, then that means that A1 plus A2 is equals to 90 degrees, right? But then I think we have the value of A1. We calculated it in 10.2, right? 90 minus X. So we're gonna have 90 minus X plus A2 being equals to 90. So A2 is equals to 90 minus 90 plus X. It's easy to see that A2 is equals to X. So since C is equals to X and A2 is also equals to X, we can go ahead and conclude that AD is indeed a tangent, right, to that circle that is going through ACF. Alright, and the moment we've all been waiting for, 10.4. So 10.4, we're given that CF is equals to 6 units. So let me just get rid of all this so that we can have a bit of clarity. So CF is equals to 6 units. So we have 6 units here. And then AB is equal to 24 units. So this is 24 units. And then let's calculate, given reasons, the length of AA. So we need this entire line here. This entire line. Right. So what can we do here? Just pause the video and try, thinking about which approach we can use to answer this question. Right? We've already established that AF is equals to FE because the line from center perpendicular to the chord bisects the chord, right? That is theorem 1. So AF is equals to FE. But at the same time, we can say that AB is equals to twice FM. We can say that this side here, AB, is equals to 2 times FM. Why are we saying that? We have a triangle, right? ABE. And then in this triangle ABE, FM is cutting the sides of triangle ABE proportionally, right? So from there we can say that AB is parallel to FM. But then it doesn't only cut the sides of ABE proportionally. It cuts the two sides into equal lengths, right? That is why we're now saying AB is equals to 2FM. That is from proportionality, right? So if AB is equals to 2FM and we know that AB is equals to 24, then we conclude and say that FM is equals to 12 units, right? So we have 12 right here. Let me just replace these and put 12 right here, and just like that we are almost done, right? Let me show you what I'm talking about. CM is equals to EM is equals to 18 units, right? That is because they are all radiuses, right? Radiuses are equals to each other. So from M to E is 18 units, right? So we have 18 as our hypotenuse, we have 12 as our opposite, so we can find FE, which is our adjacent, right? And then from finding FE, we just have to multiply it by 2 to find AE. So in triangle FME, we can say that FE squared plus MF squared is equals to ME squared, right? So what is FE? That's what we're looking for. So we're gonna have FE squared being equals to ME squared. So we have 18 squared minus MF squared, which is 12 squared. And then if you put that in your calculator, you're gonna get FE being equals to 6 square root of 5. We already took square roots on both sides, right? And then if you multiply that by 2, you're gonna ultimately get AE being equals to 12 square root of 5. From the question statement, we know that our circle is centered at O. So let's go ahead and write it down. We have a center at O. What else do we know? We know that UV is a tangent to the circle at P. So we have tangent as another keyword that you are interested in. We are also told that SP is equals to SR. So we have SP being equals to SR. If you look at your diagram, you're gonna realize also that OP is equals to OR because they are radiuses. So OP is equals to OR. Look at the vertices of PSRQ. They lie on the circumference of the circle. So we have a cyclic quad. This is all we needed to answer all the questions that are gonna follow. Let's look at 8.1.1. The question is saying, let's determine, given reasons, the size of angle PSR. So PSR is this angle right here. Right, let's go ahead and look at the first keyword, center. Well, if we add the size of O1, then O1 should be 2 times angle PSR. But we don't have the size of angle O1, so we cannot use that to determine PSR. Tangent. This angle here should be equals to PSR, but we don't have that angle as of yet, so we cannot use that to find angle PSR. SP is equals to SR. It will be easy to find the size of that angle if, for instance, we had P4 or we had R3, right? And then OP is equals to OR. It has nothing to do with that angle. And then the last keyword is cyclic quad. And as you can see, angle WQP, this angle here of 106 degrees, should be equal to angle PSR. An exterior angle of a cyclic quad is equal to interior opposite. So we can say that PSR is equal to 106 degrees. That is because an exterior angle of a cyclic quad is equal to interior opposite angle. Let's move to 8.1.2. So in 8.1.2, we're looking for the size of angle R3. We're looking for the size of angle R3. So let's replace angle PSR with 106. Let's replace that with 106. So we have 106, and we're looking for the angle for the size of angle R3. R3 should be equals to P4, angles opposite equal size. So what does that mean? It means that P4 is equals to R3. Let's start here first, and then we can see that angles opposite equal size, they should be equal to each other. So now we can say that P4 plus R3 plus PSR is equals to 180 degrees, the sum of angles on a triangle. And then P4 is R3, so we basically have 2R3 plus PSR, which is 160 degrees, being equals to 180 degrees. So R3 is equals to 180 degrees minus 160 degrees divided by 2. And then if you put that in your calculator, you should get 37 degrees. So that is the size of angle R3 and P4, because R3 is equals to P4. Let's look at the question that follows, P5. So we're looking for the size of angle P5. Right, let's go back to our keywords, because that's the only thing we're supposed to use. Can we use the center to find the size of angle P5? Well, not quite. Can we use the tangent? Let's go ahead and find out. We have the tan chord theorem. So angle P5 should be equals to angle R3. Angle P5 should be equals to angle R3. That is the tan chord theorem. Yeah, the angle between the tangent and the chord should be equals to the angle subtended by that chord on the circumference of the circle. So 8.1.3, we're saying that P5 is equals to R3 because of the tan chord theorem. So P5 is actually 37 degrees. Let's move to 8.1.4. 8.1.4, we're looking for the size of O1. Well, like we have already deduced earlier in the video, we have said that O1 should be equals to 2 times angle PSR. Yeah, the angle at the center is twice the angle at the circumference, if they come from the same arc. So O1 is equals to 2 multiplied by PSR. So this is just 2 multiplied by 106, which is equals to 212 degrees. So O1 is equals to 212 degrees. Reason being that the angle at the center is 2 times the angle at the circumference. You have to give reasons for all the statements you're making. Let's look at 8.1.5. So 8.1.5, we're looking for the size of angle P3. Looking for the size of angle P3. Yeah, that should be easy to compute. Why am I saying that? P3 is equals to R2 because they are all radiuses, right? They are all radiuses. And then if we have the size of angle O1, then we have the size of this angle POR. So we can say that POR is equals to 360 minus 212 degrees, because the angle around the point is 360. That is 148 degrees. So now in triangle POR, we can say that P3 plus R2 plus 148 is equals to 180 degrees. But P3 is equals to R2. So we can go ahead and say that 2P3 is equals to 180 minus 148. We divide both sides by 2, and P3 should be equals to 180 minus 148. That will be 32 divided by 2, should be 16 degrees.
When it comes to cycle geometry, getting the keywords right from the statement is the most important thing, because with the keywords, you are then able to answer all the questions. If you're wondering why I'm starting with 8.2, 8.1 was saying let's prove the tan chord theorem, and we've already done that.
I will leave the link in the description. In the diagram below, PWRS is a cyclic quadrilateral. So cyclic quadrilateral, I'm writing that down. So we have cyclic quad, and then the circle is centered at O. PSW is an equilateral triangle. So I have triangle PSW, which is equilateral. So when a triangle is equilateral, all the angles are equal. The only way all the angles can be equal is if all the angles are equals to 60 degrees. TW is a tangent to the circle, so we have tangent. And then we have radii OR, right? Radius OR, so let's say radii. And then OW are drawn, and then we are told that W1 is equals to 25 degrees. So all the questions that we are going to answer, we are going to stick to these keywords, except from basic things like angles on a straight line and so on. So 8.2.1 A says determine given reasons the size of S1. So we are interested on S1. Yes, S1 here. So how can we use cyclic quad to determine S1? S1 is not a complete angle, right? So I don't see how we can immediately jump to S1. The next keyword talks about triangle PSW being equilateral. S1 is not in that triangle, so I don't see how we can use that. And then the third point talks about the tangent. We have tangent TW, right? And this is how we are going to determine S1. Look at W5. W5 is between TW and RW. And then at the same time, RW subtends S1. So S1 will be equals to W5. It will be equals to 25 degrees. And why are we saying so? Tan chord theorem. And then let's move to B. B says let's find O1. Again, we're not thinking about anything else other than the four keywords we have. Cyclic quad, there's no immediate connection between O1 and the cyclic quad. Angle PSW, O1 is not an angle on PSW, right? So it cannot help us with anything. And then tangent, O1 is at the center of a circle. There's no immediate way that is connected to a tangent, right? Because usually when we're talking about tangent, we're talking about the tan chord theorem. And now the only option we're left with is radii, right? Let's look at how radii can help us. Obviously, OR and OW are equal to each other. So angle R2 will be equals to angle W3 plus W4, right? We're saying that this angle here is equals to this angle here. So now we can say that O1 is equals to 180 minus 2R2, right? Because we're gonna minus R2 and we're gonna minus W3 plus W4. But we know that W3 and W4 is equals to R2. So minus 2R2. So if we can find a way to find R2 or W3 and W4, then we can find angle O1, right? OW is a radius, right? And it touches the tangent. Where it touches the tangent forms an angle of 90, right? We know that for sure. So now we can say that W3 plus W4 plus W5 is equals to 90 degrees. I'm talking about this angle here, right? But we know what W4 is. We know what W5 is. W5 is 25 degrees, right? So we're going to have W3 plus W4 being equals to 90 degrees minus 25 degrees. And that will be equals to 65 degrees. So now in place of R2, we can put 65 degrees. So we're going to have O1 being equals to 180 minus 2 multiplied by 65, which will be 130. So O1 is equals to 50 degrees. We just stick into the keywords and nothing else. So A has 2 marks, B has 2 marks, and then C has 5 marks. And then now let's do 8.2.2. 8.2.2 says, let's prove that SP is parallel to TW. So we're proving that SP is parallel to TW. Obviously, we don't have coordinates here, so there's no way we're going to be calculating the gradient. We have to do that using angles some way, somehow. So if these two lines are parallel, then this angle here, W1, should be equals to this angle P here. But then at the same time, W1 should be equals to S2. Why are we saying that? To our keyword again, tangent. We're using the tan chord theorem, right? We're sticking to the keyword. So now we can say that W1 is equals to S2. We already said that S2 will be equals to 60 degrees, right? Why are we saying S2 is equals to 60 degrees? Because triangle PSW is an equilateral. So W1 is equals to S2, but S2 is equals to SPW. They are angles on an equilateral triangle, and all those angles will be equals to 60 degrees. And we're done with 8.2.2. We can give a reason and say that they are alternate angles.
Always the center of the circle, MNPR, is a cyclic quadrilateral, right? So let's just highlight MNPR. So we're saying that MNPR is a cyclic quadrilateral, and SN is the diameter. So we have SN is the diameter there, and then we have called MS and radius OR, right? So let's jot down our keywords, right? We know that we can use the properties of a cyclic quad, right? And then what else do we have? We have diameter. We know that it subtends an angle of 90 degrees on the circumference of the circle. And then we have chord, right? Equal chords, subtend equal angles, and so on. And then we are told that M2 is equals to 64 degrees. I think now we can answer our question. 8.1.1 says that let's determine, given reasons, the size of the following angles. And then we start in with P, right? P is this angle here. But because we know that MNPR is a cyclic quad, then P plus M2 should be equals to 180 degrees, right? That's a property of a cyclic quad. So we have M2 plus P being equals to 180 degrees, right? Opposite angles of a cyclic quad sum up to 180, right? And then what is the size of M2? M2 is 64 degrees, and then plus P, which we're looking for, being equals to 180 degrees. So now it should be easy to see here that P is equals to 116 degrees, right? And then 8.1.2 saying that let's determine the size of M1. So M1 is this angle here, right? So let's go to our keywords. We've used a cyclic quad already, and then M1 has nothing to do with the cyclic quad, right? So now let's use the keyword diameter, right? If we use the keyword diameter there, we'll see that M1 plus M2 should be equals to 90 degrees, right? Because they're being subtended by diameter SN. So now we're saying that M1 plus M2 should be equals to 90 degrees, right? Why are we saying that it should be close to 90 degrees? Because it's being subtended by a diameter, right? So now we can say that M1 should be equals to 90 degrees minus 64 degrees, right? That is M2. So M1 should be equals to 26 degrees. And the last one, 8.1.3, we're looking for the size of O1, right? If we come to our keywords here, the only keyword that we have left is chord, right? But it won't help us with much. But what I want you to realize here is that O1 should be twice M1, right? We're saying that O1 here should be twice
M1, right? Because an angle at the center of the circle is twice the angle at the circumference if they are from the same arc, right? You can see here that O1 is a consequence of SR here, and the same is true with M1, right? O1 is at the center and M1 is at the circumference. So now we can say that O1 is equals to 2 multiplied by M1. But what is M1? M1 is 26 degrees, right? So 2 multiplied by 26, that should be 52 degrees. This is the easiest question because all the answers are given to you on the statement, right? So let's look at this. In the diagram below, BOA is a diameter. We know that in Euclidean geometry, a diameter is important to us, right? So let's take that as a keyword and write it down. So we have diameter, right? And then it goes on to say that of the circle centered at O, BA is a tangent. So let's write that down, tangent, because we know that we have the tan chord theorem, and where the tangent and the radius meet, we have an angle of 90. Now let's go on and see what else we have. We are told that EA cuts the circle at D, right? And then F is the midpoint of AD. So let me show you what we're talking about. So EA cuts the circle at D, and then F here is the midpoint of AD. If F is the midpoint of AD, then this angle here should be 90 degrees, and this angle should also be 90 degrees because of theorem 1. So let's write that down. We also have theorem 1. And then that's all the information we have, right? We don't have anything else. So we should be able to get the 11 marks for this question only using these 3 statements. So let's see what happens. We have 9.1.1, which says that let's prove given reasons that OBEF is a cyclic quadrilateral. OBEF is a cyclic quadrilateral, right? So let me just highlight OBEF. So here's OB, and then we have EF, and this should be a cyclic quadrilateral. So back to the definitions, right? If it's a cyclic quadrilateral, then what should happen? O1, right? This angle O1 should be equals to this angle E. The exterior angle should be equals to the interior opposite, right? Or F1 should be equals to the entire of B. That's if indeed it's a cyclic quad. So that's what we're essentially trying to prove. And then how are we going to prove it? We are going to stick to these 3 keywords that we have. So let's look at the diameter, right? Because the first keyword is diameter. So we have our diameter OB. Our diameter subtends angle D, right? Which is 90 degrees. But then that's all it does. It has nothing to do with what we're trying to prove, right? So at this point, our diameter is failing us. Let's move to the tangent. So we have the tangent EB, right? Which is subtending A. So now we can say that angle B2 is equals to A, but then that doesn't help us with anything, right? So we cannot use the tangent to answer this one. Let's look at theorem 1, right? So by theorem 1, we have already said that this angle F1 here is 90 degrees, right? We know that F1 is supposed to be equals to the entire of this angle B here, right? So now let's just say that F1 is equals to 90 degrees. Why are we saying so? We have a line from the center to the midpoint of a chord, right? That angle there should be 90 degrees. But then we need the entire of angle B to be also equals to 90 degrees. And then we will have proved that OBEF is a cyclic quadrilateral. And indeed, we can say that our angle B is equals to 90 degrees. And then you might be asking why. Why are we saying that? That is because the tangent will always be perpendicular to the radius, right? So that angle there should be equal to 90 degrees. So since angle B is equals to angle F, we have our cyclic quad because an exterior angle will be equals to opposite interior angle, as you can see. And then now let's do 9.1.2. So for 9.1.2, we're supposed to prove given reasons that triangle ADB B, it's similar to triangle BDE. And let me tell you something, right? So the way they name their triangles in an examination, right? Angle A here should be equal to this angle B on the other triangle, and then angle D should be equal to angle D on the other triangle, and then consequently B and E should be equal to each other. So what are we saying? We're saying that let me just highlight the triangle so that we can have a bit of clarity, right? So we want triangle ADB, right? So let me highlight that. So we have triangle ADB, and then there we go, and we're also looking for triangle BDE, right? So we have BDE, right? So we're saying that angle A should be equals to angle B. So let's look at angle A here. Here we have angle A, right? We're saying that it should be equals to this angle B here. So let's go to our keywords and see which keyword we can use. You can already see that we're going to use the tangent, right? Because EB is a tangent and BD subtends angle A, right? So already here we can say that angle A is equals to angle B. And then why are we saying that? This is because of the tan chord theorem, right? And then now we can go ahead and see that angle D in triangle ADB is equal to angle D in triangle BDE. So we're saying that this angle here should be equal to this angle here, right? Which keyword are we going to use? We have diameter, tangent, and theorem 1. We're going to use diameter in this question, right? Why are we saying diameter? Because D1 is equal to 90 degrees. Why are we saying is equal to 90 degrees? It's being subtended by a diameter, right? But then at the same time, D1 plus D2 should be equal to 180 degrees, right? This is the sum of angles on a straight line, right? The sum of angles on a straight line. So you can see here that consequently D2 will be equals to 180 minus 90, which is just 90 degrees. So now D1 is equals to D2. They're all equals to 90 degrees, right? It becomes easy to see now that this angle here B1 should be equals to the angle E, because they are the only remaining angles, right? So now we can say that B1 is equals to angle E, right? But then you don't have to say this, but then I'm just assuming that we might need to use it when we solve other problems. Let's move ahead with our equation. So we have 9.1.3. So 9.1.3 is saying, let's prove given reasons that OB is a tangent to the circle passing through BDE. So let's construct that circle so that we can have clarity, right? So we want a circle passing through BDE. So it's a circle that looks something like this. It's passing through B, it's passing through D, and then it should pass through E. So it's a circle like that, right? And now we have to prove that OB is a tangent. If OB is indeed a tangent, then the tan chord theorem should hold. This angle here, B1, between a chord and the tangent should be equal to this angle E here, right? Which is subtended by that chord. How can that be true? That's what we were talking about in 9.1.2, right? That the two angles of those two triangles are equal to each other. So the remaining two should also be equal, because all those angles add up to 180 degrees in a triangle, right? So now we're just going to say that B1 is equal to angle E. And then why are we saying B1 is equal to angle E? Because third angle in a triangle, right? The third angles in a triangle should be equal to each other if the other two are equal to each other. And then where is the privilege to say that coming from? It's coming from the fact that triangle ADB is clearly similar to triangle BDE, right? Like we just proved. And now we can do 9.2, right? So 9.2 says that let's prove that OF squared is equals to AD, not triangle D, but AD multiplied by DE divided by 4. So as soon as you see a question asking you to prove something like this, right? It's either you have parallel lines or you have similar triangles. If you have parallel lines, then you can play with the sides. If you have similar triangles, then you can play with the sides, right? So clearly here, we have similar triangles, so we're going to use them, right? If we had parallel lines, we're going to use the parallel lines. We know fully well our theorems. So let's look at the sides we're interested in here. We're interested in AD, DE, and OF, right? We have triangle ADB, and here we have triangle BDE, right? And then which sides are we looking for? We're looking for AD and DE. So because the two triangles are similar, we can say that line AD, right, on this first triangle here, divided by line DB on that triangle will be equals to line BD, right, on this triangle here, divided by line DE, right? The sides will be in proportion because the two triangles are similar, right? And then we must state here that we're saying that because we know fully well that triangle ADB is similar to triangle BDE, right? So now we can cross multiply, and then we can get DB squared is equals to AD multiplied by DE, because look here, DB is just BD, right? So we can just say DB squared is equals to AD multiplied by DE. And then we're not done, right? Here we have DB squared, but in what we are required to prove, we have OF squared, right? So let's try and find how DB squared and OF squared are related. It's not really easy to see here, but then 2OF is equals to DB. Let me tell you why, right? Don't forget that we have already deduced that F1 is 90, right? But then also D1 is 90. Because it's been subtended by the diameter, right? So if F1 is 90 and D1 is 90, then we know that OF should be parallel to DB, right? OF is parallel to DB. But because F is the midpoint of AD, then we have AF being equals to FD. If AF is equals to FD, then OF should be half of DB. So that is why here I'm saying that 2OF is equals to DB, right? So if we substitute that back in our equation, we're going to get 2OF squared being equals to AD multiplied by DE. So it should be easy to see now that we're going to get 4OF squared is equals to AD multiplied by DE. So now we're dividing both sides by 4, right? If we do that, we get OF squared is equals to AD multiplied by DE, and then everything divided by 4. Let's see what's happening here. So in the diagram, PQRS is the cyclic quad. So let's indicate that, right? We have PQRS being a cyclic quad. I'm just going to write that down too, because a cyclic quad is very important to us, right? There's a few properties around that. And then KP is a tangent, so let's have a tangent there. And then what else do we have? We are told that CA is parallel to QS, so we have parallel lines. And then P1 is equals to R2, right? So what I've been proposing is that with only these 4 keywords, we should be able to, answer all these questions that we have, right? So let's go ahead and give it a try and see what happens. So the first question, 10.1, is saying that let's prove, given reasons, that S1 is equals to T2. And yeah, indeed, S1 is equals to T2. Let me show you how. So let's look at S1. S1 is here, right? Is an exterior angle of a cyclic quad, right? We're using our first keyword there. So if it's an exterior angle of a cyclic quad, it should be equals to Q1 plus Q2, right? So S1 is equals to Q1 plus Q2, right? An exterior angle of a cyclic quad is equals to interior opposite, right? Yeah. So we have exhausted the cyclic quad. Now let's look at T2, right? Because we're supposed to prove that S1 is equals to T2. S1 has no immediate connection with T2, right? So let's try other ways here. When I look at T2, I realize very quick that T2 should be equals to R2 plus Q2, right? An exterior angle of a triangle is equals to the sum of the two interior opposite, right? So what are we saying here? We're saying that T2 will be equals to R2 plus Q2, an exterior angle of a triangle is equals to those two interior angles, right? So from here, where do we go? We can see that S1 is equals to Q1 plus Q2 and T2 is equals to R2 plus Q2, right? Let's go to our next keyword. We have the keyword tangent, right? Let's see what it can give us. So from the keyword tangent, we will see immediately that P1 here is supposed to be equals to Q1, right? P1 is supposed to be equals to Q1, right? Because of the turn-chord theorem, right? Because of the turn-chord theorem. So let's write it down. Let's say that P1 is equals to Q1 because of the turn-chord theorem, right? So from here, what can we say? Let's look at the keywords again. With parallel lines, they won't give us much, but if you see here, we are told that P1 is equals to R2, right? P1 is equals to Q1, but then on the statement itself, we are told that P1 is equals to R2. So what does that tell us? That tells us that R2 is equals to Q1 because they are all equals to P1, right? So now you should be able to see here, let me show you something. Now you should be able to see here that instead of R2, we can write Q1 because we have proved that R2 is equals to Q1 because they're all equals to P1. So instead of R2 plus Q2, we can say Q1 plus Q2, right? So now it will be easy to see here that S1 is Q1 plus Q2 and T2 is Q1 plus Q2. So we have proved that T2 is equals to S1 since they are all equals to Q1 plus Q2. And yeah, you get your 4 marks. And now let's move to 10.2. So we are at 10.2 now. So 10.2 is saying that let's prove given reasons that AD divided by AR is equals to AS divided by AC. So let's go and look at those lines and see what's happening, right? Are we going to use parallel lines or do we have to prove that certain triangles are similar to each other? Let's go to our sketch. Yeah, so we have AD. Where's AD? Yes, AD here, right? So AD divided by AR, right? Divided by AR is said to be equals to AS divided by AC. So we have AS here divided by AC, right? So I can see immediately here that this is all going on in two triangles, right? In triangle, not A, but triangle. In triangle ASD and triangle ACR. So if we can prove that triangle ACD and triangle ACR are similar to each other, then we can play around with their sides, right, and be able to prove that. So let's go ahead and prove that triangle ACD and triangle ACR are similar to each other. Even when you look at them, right, they do look similar. But we have to prove we're not trusting our eyesight here. We actually have to prove that they're similar to each other. So real quick, you can see here that, let me just erase this line. So you can see here real quick, right, that A is a shared angle of the two triangles ASD and the triangle ACR, right? A is a common angle. So we can say that angle A is equals to angle A, obviously, right? It's a common angle, right? There isn't really much to say there. So from here, where do we go? Let's see. So here we are expecting angle S1 to be equals to angle C2, right? Because of just, how the triangles are. So let's, give it a look and see how we can potentially prove that. So we already know from 10.1 that S1 is equals to T2, right? But then, since these two lines here are parallel to each other, then T2 should be equals to C2, right? Because they are, is it called alternating, corresponding? I forgot the name, but it's called something. We know that C2 is equals to T2, right? And then you're gonna give that reason there. But you know what's going on. There's some reason there why T2 is equals to C2. It's because of the parallel lines for sure, but there's a specific reason why we say those are true. So now, since we've proved that T2 is equals to C2, we can conclude that D1 should be equals to R1. Why is D1 equals to R1? Because the third angle of triangles, right? If the other two angles are equals to each other, then consequently the third angle should be equals to each other. So we've proved that ASD is similar to ACR, right? So let's look here. ASD is similar to ASR. So now we can say that AD, right, divided by AR is equals to AS divided by AC, right? We can only have those lines if we've proved that those two triangles are similar to each other. So what are we saying now? Now we're saying that AD divided by AR can be equals to AS divided by AC if and only if triangle ASD is similar to triangle ACR, and that's how we do 10.2, right? So now let's look at 10.3. So 10.3 say that let's prove that AC multiplied by CD is equals to AR multiplied by TC. In this question, I cannot see an immediate way why AC multiplied by CD should be equals to AR multiplied by TC. But you just wrote this paper today. If you have an idea, let me know in the comments. 9.2.1, let's prove that OTBG is a cyclic quad. So we're talking about OTBG. We need OTBG to be a cyclic quad, right? But then what does it mean when OTBG is a cyclic quad, right? That quadrilateral should fit on a circle, right? And then all the vertices must lie on the circumference of the circle. So we must be able to draw a circle, right? Obviously, I'm not going to do any justice drawing the circle, but we must be able to have something of this manner if OTBG is a cyclic quad, right? B is also lying on the cyclic quad. Yeah, that's what we mean when you say OTBG is a cyclic quad. So when I tried solving this problem, the mistake I made, I tried proving that it's a cyclic quad by saying that this angle here plus this angle here, they should be equals to 180. That is correct, right? And then another way I try to prove it is that this angle here should be equals to that angle there. And then I couldn't prove it using those two ways, right? I'm not saying those ways are not correct. They're correct, but when I try proving that OTBG is a cyclic quad using those ways, I couldn't, right? And then what helped is realizing that if OTBG is a cyclic quad, then this angle here, GBT, this angle GBT should be equal to the angle GTO, right? Why should they be equal to each other? Because they're being subtended by the same chord GO, right? So if we prove that those angles are equal to each other, then we have proved that OTBG is the cyclic quad. So let's go ahead and try that. So let me just erase this. So we are required to prove that angle GBO is equals to angle GTO. If we can prove that, then indeed OTBG is a cyclic quad, right? So let's go ahead and try and prove that. So very quick, you can see here that this line from the center is cutting the line EF in half, right? If it cuts the line EF in half, then this angle here should be 90 and this angle here should also be 90. So what are we saying? We're saying that GTO, yeah, that's correct, is equals to 90 degrees, right? The line from the center is bisecting the chord, right? So that angle there should be 90 degrees. So now we know fully well that GBO should also be 90 degrees, and indeed it is. We're going to say that GBO is equals to 90 degrees. Why are we saying GBO is equals to 90 degrees? Because this radius here will be perpendicular to the tangent, right? We know that fully well. So the radius is perpendicular to the tangent, right? So now we've proved that GTO is equals to GBO because they're all equals to 90 degrees, right? And then as a consequence, OTBG is a cyclic quad, right? It's a cyclic quad because clearly GBO and GTO are lying on the same segment. Now we can do 9.2.2 because we have proved beyond reasonable doubt that OTBG is a cyclic quad. So 9.2.2 is saying that let's prove that GOB. So let's just get rid of that. We have GOB here. So here's GOB. We're supposed to prove that apparently GOB is equals to angle S, right? But then immediately when you look at this, you would think that angle S is equals to angle STF, right? Because they are alternating. So let's just write that down. So we're saying that angle S is equals to angle STF because they are alternating angles, right? If you just look at that. But then if you look at STF, you will see that STF is equals to GTB, right? GTB. So we say that angle S is equals to, not angle S, but angle STF. So angle STF is equals to GTB because those are vertical opposite angles, right? Yeah, whatsoever the reason is. Yeah, we know that STF should be equals to GTB, right? But I kid you not, GTB should be equals to GOB, right? GTB is being subtended by GB, right? And then GOT is also being subtended by GB. We've proved that OTBG is a cyclic quad, so we can get away with saying that, right? So here we're gonna say that they've been subtended by the same chord, right? By the same chord. Yeah. So now you can see that we're saying that GOB is equals to GTB, and here we say that S is equals to STF, but STF is equals to GTB. So now we can say that angle S is equals to angle GOB. Why are we saying that? They are all equals to angle GTB. How do you know which theorem you're supposed to use? You go through the question statements and you're going to be guided by the keywords, right? And then from the keywords, you shall be able to answer all the questions, only sticking to that. So let me show you what I'm talking about. In the diagram, O is the center of the circle. So there's a keyword, center of the circle, because we know that there's a few things we know about the center of the circle. And then it goes on to say that EC is a tangent to the circle at C. And then another keyword is tangent, right? We know that there's a theorem around the tangent. Diameter DB is produced. And then again, we have diameter because, yeah, that is important to us here. And then what else do we have? BF is said to be perpendicular to EC. Radius CO produced bisects AD at G, BC and CD at all. When the radius bisects AD, so here's AD, right? That is theorem 1 or the converse. So we have theorem 1. So yeah, we shall be able to answer all our questions only using these 5 keywords, right? So let's go ahead and see if that will work. So we have 10.2.1 as the first question. So the first question is saying, let's prove given reasons that this line FB, so where is FB? FB is right here, is parallel to line CG. So let's go ahead and see if the first keyword, center, can help us in any way, right? I cannot see a direct way in which the center would help us. So let's go and move. So let's move to tangent and see if we can do something there. The only thing we can deduce from the tangent is that this angle here is 90 degrees, right? Because the tangent and the radius will always be perpendicular to each other when they touch, right? So we can say that angle BC, BCO is equals to 90 degrees. And why are we saying so? We know that the tangent is perpendicular to the radius. But then we are given that F1 is equals to 90 degrees, right? Right here, F1 is equals to 90 degrees. So you can see now that we have two corresponding angles. So the two lines must be parallel to each other. So right now we're going to go ahead and say that F1 is equals to angle BCO because they are all equals to 90 degrees. So as a consequence, we can conclude and say that FB is parallel to CG as we have corresponding angles, right? And then now let's do 10.2.2. 10.2.2 says let's prove that triangle FCB is similar to triangle CDB, right? So let's just sort of highlight our triangle so that we can see what we're talking about. So we have FCB and triangle CDB. So it's the CDB. So we're going to prove that these triangles are similar using angle. Let me show you what I'm talking about. When they name their triangles in this question, they name them such that this angle F here in FCB should be equals to angle C in CDB, right? So we're saying that this angle right here, F, should be equals to this angle right here, right? So let's see how we can prove that, right? We actually going to use the diameter to deduce the size of this angle here, right? Because it's being subtended by the diameter. So we can say that angle C1 plus C2 is equals to 90 degrees because it's being subtended by the diameter. And now we need to prove that this angle here is also 90 degrees, right? How can we do that? We can say that F1 plus F2 is equals to 180, but F1 is 90 degrees, right? So F2 should be equals to 90 degrees. You know, this is the sum of angles on a straight line. Now we've proved that those angles are equal, and we can go ahead and find another pair. So now we're going to go to angle C in triangle FCB and angle D in triangle CDB. So where is angle C in triangle FCB? Angle C is right here, right? We're supposed to prove that it is equal to this angle right here. And it is easy to see that angle C1 is between the tangent and the chord, right? And then this chord is subtending this angle D2, right? So that is the tan chord theorem. So we can go ahead and say that angle C1 is equal to angle D2 because of the tan chord theorem. Right? So now we've proved that two pairs of angles are equal. We just left with the third one. And then now, lastly, we can say that angle FBC, this third angle here of triangle FCB, is equals to angle B3, which is in triangle CBD, right? Why are we saying that third angle of a triangle? If the two other angles are equal to each other, then the third angles should also be equal to each other, because the sum of angles on a triangle is the same, right? So yeah, now we have proved that indeed triangle FCB is similar to triangle CDB, because angle, yeah, all those angles are equal to each other, right? And 10.2.2, let's give a reason why G1 is equal to 90 degrees. So let's go ahead and look at where G1 is located. So G1 is right here. Yeah, let's give a reason why it is equal to 90 degrees. That is theorem 1, right? So the reason is that a line from center to midpoint of chord is perpendicular to the chord. And then if it is perpendicular to the chord, then consequently G1 should be equal to 90 degrees, just like G2. Right, that is theorem 1. And then now 10.2.3. Let's prove with the reasons why CD squared is equal to CG multiplied by dB. So what I like doing here is to write CD as CD multiplied by CD being equal to CG multiplied by dB, just to have a bit of clarity. Let's go ahead and highlight these sides so that we can see which triangles we're interested in. So I'm just gonna remove all that. So we have line CD. So here's line CD. Let me just highlight it so that we can see what we're talking about. And then we have line CG. So I'm just gonna highlight it also. So we have line CG right here, right? So let me just highlight it. And then we have DB. Where is DB? Yeah, DB is right here. DB is right here, right? So we can close this triangle here, and we can close this triangle here. So it looks like we're interested in triangle CGD and triangle CBD. So if we prove that these two triangles are similar to each other, then we can play with the proportions. So let's look at triangle CGD. You should be able to see real quick here that G2 here is 90 degrees, right? And then this angle C2 plus C3 is also 90 degrees because it's been subtended by a diameter, right? Now we just need to prove that two other angles are equal to each other and the two triangles will be similar. We can now attempt to prove that this angle D2 here is equal to this angle C3, right? Yeah, D2 is in triangle CBD and C3 is in triangle CDG. So we have already said that C1 is equal to D2 because of the tan chord theorem, right? So if we prove that C3 is equals to C1, then we are basically saying that C3 is equals to D2. But how can we do that? So C1 plus C2 is equals to 90 degrees because the tangent is perpendicular to the radius. But then C2 plus C3 is equals to 90 degrees because they're being subtended by the diameter, right? So as you can see here, C1 plus C2 is 90, C2 plus C3 is 90. So clearly C3 is equals to C1 because when you add them to C2, they're giving you 90 all the time. But then we know that C1 is equals to D2. So C3 is equals to D2. And then angle BCD is equals to angle CGD because they are all equals to 90 degrees, right? We have talked about why that is the case. So we can go ahead and say that angle B3 is equals to angle D2 plus D1 being the third angle on the triangles, right? So now we can conclude that triangle CGD is similar to triangle CBD, right? And then if we prove that, we can then say that CD divided by DB is equals to CG divided by CD. If we cross multiply, CD squared is equals to DB multiplied by CG, right? This is CG right here. KLMN is a parallelogram and the diagonals intersect at point P. So right here, this is where the diagonals intersect, right? And then NM is produced to S, R is a point on KL, and then others cuts PL at T. And we are told that NM is to MS is 4:1, NL is equals to 32 units, and TL is equals to 12 units. So the first question, 9.2.1, it is saying that let's determine with reasons the value of the ratio NP is to PT in its simplest form. So let's look at NP is to PT. So we have NP right here, and then PT is right here. So if these two lines were parallel, these two lines, then we would say that NP to PT is just 4:1, right? But then we are not given that information. We cannot just conclude that the line KM is parallel to RS. So we have to use something else. But what do we use, right? We are told that NL is equals to 32 units, right? So this entire diagonal is equals to 32 units. But then the diagonals intersect at P. That tells us that we have 16 units here, and we have 16 units on this side. So now we can see fully well that NP is equals to 60 units, right? Because where the diagonals intersect will be the midpoint of both diagonals, right? And then now if we find PT, we would essentially be done, right? So from T to L is 12 units, but we need PL to be also equals to 16, right? So that tells us that PT is equals to 4 units. So we can say that PT is equals to 4 units, right? So now it will be easy to see that NP is to PT is 16 is to 4. But then if we simplify 16 is to 4, we get 4 is to 1. So that is the ratio of NP to PT in its simplest form, right? Now let's see if we can do 9.2.2. So 9.2.2 is saying let's prove with the reasons that KM is parallel to RS. Now we have to prove that KM is parallel to RS. Let me just remove this line. So we're saying that we're supposed to prove that KM is parallel to RS. So these two lines are parallel, right? We know that NM to NM is to MS is 4:1. And now we have proved that NP to PT in its simplest form is 4:1. These two are equal. So we can say that KM is indeed parallel to RS. The two lines, they divide the size of triangle NTS in proportion, right? That is the converse of the proportional theorem, right? So that is our answer for 9.2.2. And then now 9.2.3, if NM, so we have NM is equals to 21 units. So NM is equals to 21 units. Then let's determine with reasons the length of RL, right? So NM from here to here we have 21. But then since KLMN is a parallelogram, then it means that KL is also 21 units. So in pursuit to find RL, let's try use KL, because we know that KL is equals to 21 units, right? So we're going to say that NM is equals to KL is equals to 21 units in triangle KPL. So we're interested in this triangle KPL, right? These two lines are parallel, let's not forget. So we can say that RL divided by KL is equals to LT divided by LP. So we're looking for RL. We know that KL is 21, right? And then LT, so LT is 12 units, and then LP is 16 units. So RL will be equals to 21 multiplied by 12 divided by 16, which is equals to 15.75 units. So let's give a reason why DE is parallel to BH. So let me just highlight DE real quick. So we have DE here, and then BH is this line here. So we know fully well that if a line parallel to one side of a triangle, so this line DE here, if it's parallel to BG, then it should divide the other two sides proportionally, right? We can see here clearly that for 8.2.1, AD divided by DB should be equals to AE divided by EG, right? Because AD is equals to DB and AE is equals to EG. So we can conclude and say that DE is parallel to BH because it divides AB and AG proportionally. Now let's do 8.2.2. So 8.2.2 is saying that if it is further given that FC divided by BF is equals to 1 divided by 4, and that DE is equals to 3x minus 1, and GH is equals to x plus 1. Let's calculate, given reasons, the value of x, right? When you just look at DE is equals to 3x minus 1 and GH is equals to x plus 1, you can think the problems are a little complicated, especially if you look at the sketch again and you look how it is. Yeah, you might get intimidated, and then you even see the mark allocation, 6 marks. But let's see what happens. So right now, we know that, let me just erase this line. So right now we know that FC divided by BF is equals to 1 divided by 4. And then we given DE, right? The length of DE in terms of variables. So we're given 3x plus 3x minus 1 there. So let me just write it down. We're given 3x minus 1 here. And then what else are we given? GH is x plus 1. So here we're given x plus 1. Okay, so now I see what's happening here. If DE, right, if this line here, DE, cuts AB and AG such that AD is equals to DB, right? You can see here, because of these lines that we given, that AD is equals to DB. If DE cuts AB such that AD is equals to DB, then we can say that BG is equals to 2 times BE, right? DE will only cut AB and AG such that AD is equals to DB if DE is half of BG, or if BG is twice BE, right? So the reason we can give here for this statement here is that AD is equals to DB, right? This statement here is only true if AD is equals to DB. So if we say that, you will realize real quick that BG now becomes 2 multiplied by 3x minus 1, right? So now using that triangle BHC, we can say that in triangle BHC, we can say that, so what do we have? We can say that FC divided by BF should be equals to GH divided by BG. And why are we saying that? We're saying that because FG is parallel to CH, right? We can only see that if we have 2 parallel lines, right? So what is FC divided by BF is given to us. We have 1 divided by 4. But what is GH? GH is x plus 1, right? And then BG is 2 multiplied by 3x minus 1, which will just become 6x minus 2. Right, so now we are actually done with the conceptualization, right? We're just computing the value of x. So if we cross multiply here, we're gonna get 6x minus 2 being equals to 4x plus 4. So it should be easy to see here that 2x will be equals to 6. So x should be equals to 3, right? We need to prove that a line from the center that bisects the chord is perpendicular to the chord. We're going to do that in 3 easy steps, right? So step number 1 is to make some construction, right? So let's go ahead and construct OA and OB. Let me show you what I'm talking about. So we are going to join OA here. So let me just do that real quick, and then we're also going to join OB, right? And now we can move to the second step, right? So the second step, we're going to prove that triangle OAD and triangle OBD are congruent. How can we possibly do that? We can start by saying that OA is equals to OB. They're all radiuses, right? So they're supposed to be equals to each other. And then now we can say that OD is equals to OD in the 2 triangles because it's a common side, right? So our reason here will be common, is a common side. And lastly, we're going to say that AD is equals to DB, right? That's given. We can clearly see on our sketch that is given to us. So if those 3 sides are equal, we can then conclude that triangle OAD is congruent to triangle OBT. And why are we saying that? Side. All 3 sides are equals to each other. And now we can move to the last step. What do we know about perpendicular lines? We know that if 2 lines are perpendicular, then where they touch, they should make an angle of 90, right? So if we can prove that we have 90 right there, then beyond reasonable doubt, OD is perpendicular to AB. So let's call this angle here D1 and call this angle here D2 as part of our constructions. But we know that D1 is supposed to be equals to D2. Why am I saying that? Triangle OAD is congruent to triangle OBD, right? All corresponding angles should be equals to each other. So D1 should be equals to D2, right? But then it's easy to say that D1 plus D2 is equals to 180 degrees, right? As they are angles on a straight line. But D1 is equals to D2, so we can just say that 2D1 is equals to 180 degrees. So what are we saying? We're saying that D1 is equals to 90 degrees. So now we have proved that D1 is 90 degrees. We're gonna know fully well that consequently D2 is also equals to 90 degrees. Now we can conclude and say that OD and AB are perpendicular to each other because D1 is equals to 90 degrees, right?